C'est pas bien. C'est pour.
Hi everyone, thank you to be here. Today we will listen to Today we will listen to Léo Girier, who will talk about his postdoctoral research.
Thank you, Louise, for the introduction. So what I will present you is mostly the first year work of my postdoc, which will talk about acoustic modal identification in a flow duct of varying cross-section, and with a particular application to the air intake of an aircraft engine. This work is part of a European project, Companion, which is co-funded by the European Union, and with different partners such as the LVA. So for the context, we're interested in this guy here, so aircraft engines that you can see in civil aircraft, with the architecture of what is called the turbofan. And we are mostly interested in the noise coming from the interaction of the flow with these big fan blades here, mostly. And for that, usually we develop a scaled mock-up that is put in a wind tunnel to be tested. And microphones are placed along the wall, as you can see here. And also in the side view, you can see different microphones schematically represented along the axis, and also further down the engine. So the idea is to be able to characterize the engine's noise signature by identifying the structure of the sound wave inside the engine that will help us understand what are the sources of noise. And the problematic here is that with the current trend of this type of architecture, the engine diameter tends to increase, and to compensate for the weight, its length is reduced. So in this case, we have less place to put a microphone in the air inlet because of the reduced space, which has a direct impact on the resolution of the mode identification. And also, the mean flow that is incoming in the engine is less uniform when it reaches the fan blades. So the sound propagation is in a more complex environment, and also it can lead to new acoustic sources when interacting with the fan blades. So in this context, the objective of this talk and this work is to try to characterize the dominant sound propagation mechanisms in this such an air intake, and test the relevance, measure the performance, let's say, of advanced analytical models to improve mode identification in such conditions. Okay, just to present briefly the studied air inlet. So in this view, the fan blades have been removed. So we are left only with the walls of the nacelle outside and of the hub or spinner here. And this is in this duct that we will investigate the sound propagation. And in particular, we will have access to the wall pressure along this red band represented on the figure. And if I show it in a plane, a Cartesian plane on the right-hand side, where I didn't preserve the scale between the azimuth and the axis for sake of visualization, you can see how the microphones are located, which is a constraint. It was designed in the project as is. So there is basically two rings of microphones distributed azimuthally, okay, along the circumference, and 4 lines of microphones. So based on that, the results I will show today are only based on numerical simulation as reference, because we unfortunately don't have experimental results yet. So I will start by explaining a bit the simulation that will be used as a reference before explaining the modeling of the model basis. So there is two steps for the simulation. The first one is to model the flow that will be ingested by the engine. So this is done also with some simplification compared to reality. It is based, this simulation is based on a potential flow, which means that it is stationary, irrotational, and most importantly, inviscid. Inviscid means that we neglect the viscosity in the fluid so that we don't have any boundary layers developing along the wall. That can have a drastic impact on sound propagation, actually. And for the condition of the operating condition, which is mostly the condition of the sideline acoustic certification for those who are aware of it, which is more or less representative of takeoff at full power. And then, so based on this mean flow simulation, an acoustic simulation is performed based on the linearized Euler equations, where you enforce along this plane here a boundary condition in pressure that is that describe a given mode, which is analytically known here because the flow and geometry are uniform. And enforcing this boundary condition and solving for the wave equation, you get the propagation in this complex geometry and mean flow. So that will you can have like this propagation for each mode at each frequency, and this will serve as a basis for us to see if we're able to correctly identify them and model them. Okay. So what we can see here, also for reference, I've shown in dashed black line the position of the microphone array. So this is this particular area that is of interest for us. Okay. And in this area, the mean flow is actually pretty complex, three-dimensional, varying axially, radially, azimutally. So the question is, how does it impact sound propagation? So here we take a look at the plane mode injected, in the inlet plane at two different frequencies, 1.5 kHz and 3 kHz, along this red wall band, as I mentioned earlier. So here at 1.5 kHz and 3 kHz, you can clearly see that the plane mode actually is no longer plane, clearly. So there is effect of especially the mean flow that we will try to understand and in order to capture this effect. But basically you have this kind of sinuous pattern of the front wave and also small differences in wavelength depending on if you are at the top or the bottom of the duct. So that's what we'll try to retrieve later on. But since I work mostly with analytical models, what I like to do is first try to simplify as much as possible and then add step-by-step layers of complexity in order to see how we can model a complex system. So to go back to the basics, just a quick slide to remind you of cylindrical duct modes. So here we will model a straight channel with hard walls and even without flow, okay? So in this context, we solve for the Helmholtz equation, which is the wave equation in frequency domain. So for a single time harmonic with hard wall boundary condition enforcing no flux through the wall and periodicity in the azimuth. So the solution of this is this nice looking modal solution in x, r, theta, where you have a double sum, one on what we will call azimuthal order, n, and one on the radial orders, s. So it is composed of complex coefficient, the amplitude, which relates to the amplitude of the mode, radial function depending on the Bessel function of the first kind, and involving what we will call the radial wave number, periodicity enforced in the azimuth, with the number of lobes given by the azimuthal order, n, and then an axial dependency involving the axial wave number. what is to be understood here is that these wave numbers are related through what we call the dispersion relation, where k is the frequency normalized by the divided by the sound speed. And what this tells us, this axial wave number squared, is that if it's positive, the acoustic mode related to it is able to propagate through the channel, through the duct, so it propagates energy. And if it's negative, then the mode is not able to propagate and will exponentially decay. So it will remain local. To give you a few examples, here are cross-sectional view of this mode. So for example, if you have n equal 1, you have one nodal diameter, so you have two lobes, okay? Two lobes, but one wavelength along the circumference, hence n equal 1. And for the radial order, it's the same thing, but in the radial direction. So you have one nodal circle, like in SISO, and etc., etc. When you increase this n, you have two nodal diameters, etc., until, for example, n equal 5, s equal 4 here. Okay? So pretty basics. So now we've seen that in the duct that we are interested in, there is a variation in all 3 dimensions of the duct geometry and flow. The first thing we need to look at least I propose to do that, is to try to account for the variation of the duct along the axis. So for that, I will use the slowly varying formalism, where the idea is to say that the variation of the duct geometry occurs on a much larger scale than the acoustics fluctuations, okay? So if both this scale, imagine a duct varying very slowly, where the acoustics at high frequencies varies very rapidly. If these two scales are well separated, we can make some simplification and actually end up with a closed form analytical approximate solution of the Helmholtz equation. So that's the base theory. And it is also a monomodal theory, which means that a given mode conserves its energy through the duct. Okay, it cannot scatter. Just to make it maybe a bit more visual, if you imagine this duct on the bottom side, where with a given radius function of x, what we say when we say that the duct geometry varies slowly is that we can almost consider the duct wall to be horizontal. So imagine this view of a discretized duct in different segments of constant height or constant radius, cross-section surface area. Then we see earlier the solution in this duct. So here in each segment, you know the solution, classic duct mode. The only difference is that each time you have a different radius, so the wave number are different. Okay? Well, the slowly varying formalism is basically the same, but in a continuous manner. So we don't discretize the duct, but we see it as a continuous function of x. Okay? So in that sense, we end up with a radial wave number that varies with x. Okay? So through the dispersion relation, the axial wave number also varies with x, hence this integral over x and the exponential here. And also to conserve energy, since the cross-section surface area and the wave numbers vary along the duct, the amplitude of the mode also has to vary to keep the energy constant, basically. Okay? So basically, this formalism is very convenient because you have the exact same modal structures than in a straight duct, where just the amplitude and wave numbers are now allowed to vary with the location. Okay? And just to finish with this slide, an interesting phenomenon that can be understood already is that, if you remember, this axial wave number tells us if the mode propagates or decays. But now it is function of x. So in fact, what can happen is that a mode that is propagating through the duct can at some point become what we say cut off, so decaying. And in this case, it will be totally reflected back because in this monomodal theory, the mode conserves its energy. So since the energy is no longer able to propagate, it has to go somewhere. so it goes back. In this case, you will have a standing wave pattern on the left side and a decaying mode on the right side after the transition. And we'll see just one example of such a phenomenon here. So in the simulation, I selected the mode of order 5 and 4 at 3 kilohertz. And what you see on the left-hand side is the numerical simulation, and on the right-hand side, the slowly varying model for this mode on the wall here, on the middle, and on the side view of the duct on the right-hand side. So what you see here, the darker spots are in fact the standing wave pattern, if I was able to animate it in time. And after this darker spot, you have a clear decay in amplitude, hence the lighter spot. Okay? So here, transition is happening, but it's a little bit different in the numerical simulation because we've simplified it a bit in the model. In fact, what happens in reality, and what happens also in this simulation on the left, is that when the mode transition from cut-on to cut-off, from propagating to decaying, it does not only reflect all its energy to the same mode, it in fact is able in fact to scatter some of its energy to its neighboring modes. So understand modes with a close wave number to it. And that's why you see in fact this white curve here, which is a nodal line. It's a 0 in this color map. This is a marker of multimodal propagation. In fact, you can have that only if multiple modes propagate and destructively interfere along this line to have a 0. Okay. So since we injected a single mode at the inlet plane, we know that if this happens, it means that there is the only solution for that to happen is that several modes are propagating, so a transition occurred in the simulation. So now that I've said all of that, we've seen the kind of simplification that we made in the geometry and the flow. So again, we only account for the axial variation of the duct, not the radial and azimuthal variation. And we've seen that also if something like that happens, we simplify it a little. So are we able to still identify the correct mode with all this simplification? And fortunately enough, the answer is yes. So here you can see on the left-hand side the numerically simulated pressure field that we try to retrieve with our model basis. And in black circles, the position of the microphones that I shown you before. So what we do is we take the pressure simulated only at this black circles location, and we project it into our slowly varying model basis. What it gives us is actually the same simulated mode as the dominant mode, so that's good, with almost 10 dB difference with the other mode, but not a lot. It's quite well identified. And when you use this identify modes to try to reconstruct the pressure field on the whole map, you get this plot in the middle, which is quite good, qualitatively at least, compared to the original one. Okay. And to go further into the analysis, maybe more systematic, what we can do is compare this whole pressure map to the simulated one, the reference one, and see how much of a difference there is between the two. So for that, we compute what we call the signal-to-noise ratio. So the higher it is, the better the reconstructed field, the lower, the worse. Okay. Oh, sorry, just before that, I have another slide to show you what the result would be if we have used the classical duct modes without the geometry variation. Okay. So if you use the classic duct modes, we are unable to retrieve the correct order that was simulated, and the reconstructed pressure field is very bad. Because in fact, this we don't account for the possibility of a transition in this case, so it is unable to retrieve such a pressure field. Okay, so to go back to what I was saying about the comparison between the two pressure fields, here I represented this quantity of signal-to-noise ratio versus the frequency for different modes. So in solid lines, you have the results for the slowly varying model, and in dashed line, the result for the classic duct modes. On the top left part, you have the plane mode, okay? And when you go on the first line from left to right, you increase the radial order of the simulated mode. You can see that when increasing the radial order, the slowly varying model gives better and better results compared to the classical duct mode. And on the second line, we this time vary the azimuthal order, where on the bottom right part, you have the mode that I've shown earlier, where the transition happened. And again, basically, the slowly varying formalism performs generally better than the classic duct modes when we compare the whole pressure maps, basically because it accounts for more physical mechanisms, so it is able to reproduce a little more with a little more fidelity the simulation. But it doesn't work that well for the low order modes, and I will get back to that later. Keep that in mind. Okay. Also, just to show you something that I didn't talk about, how do I solve the inverse problem? Because there is something to do here as well. And to explain that, I will show an example, of a combination of two modes, -4,0 and 7,0. And basically what we want to do is to find the complex coefficient that minimize the residuals of the system projection of the mode on the modal basis. And for that, we can use different norms. And for example, if I use the L2 norms, so the classic Euclidean norm, we see that we are unable to retrieve the simulated mode because they are almost 25 dB below other modes in the middle, which correspond to low order modes in this plot. Almost the same goes for the L1 norm using the absolute value. It is a little bit better, 5 dB higher, but still this noisy mess in the middle with the low order modes. And only when we go to infinity norm, taking the maximal value, we can start to have the simulated mode as dominant in the identification, but still a lot of other modes. So to compensate that, I had to use finally a pseudo-inverse regularized method, so with Tikhonov regularization, which basically consists in a trade-off between the residuals and the solution energy. So you have to choose a parameter that drives the regularization, basically. And if it's to 0, you minimize still the residuals. But if you allow it to be slightly higher than 0, the residuals will be slightly worse, but you will have a sharp decrease in the solution energy, which sometimes might be more physical and more consistent with reality. And in this case, so doing this regularization, we are finally able to correctly, let's say, identify the simulated modes with very less other modes in the middle. So we get them more clearly. Okay, so now that we've seen all that, what you can understand from what I've shown by comparing the classic duct modes and the slowly varying modes, then explaining to you how the inverse problem goes, you can understand that there is something happening with the low order modes that we do not very correctly identify, or not as easily as the other modes. And I want to tell you why, at least try, because it's something ongoing, let's say. So remember this mode, the plane mode injected at 3 kHz in the simulation on the left, and what the model gives on the right. So you see not much difference compared to classic duct modes, in fact. I've let this aside previously, and you will see why. Something that I have to say first is to explain a little bit why does this wiggly pattern happens within the simulation. Remember that, okay, so that's in the wrong order, I think. Remember that when we look at the flow, the mean flow computed numerically, there was a complex 3D pattern. And the modes that we are looking at are propagating upstream, so against the mean flow. And in fact, when a mode does that, its wavelength is compressed by the mean flow. So you can see here at the top of the duct in blue, we spot almost 2 wavelengths. And at the bottom, we see 2.5, more or less. And this is explained by the fact that the mean flow is not axis symmetric. It has a lower velocity at the top than at the bottom, as you can see with the darker color on this plot, which explains why we have more compressed wavelengths at the bottom on this plot, and also actually why the sinuous pattern occurs, because along its propagation, the mode will propagate faster at the top than at the bottom. Hence this wiggly pattern instead of a plane wave. Okay. Also, you can already see the axial variation of the mean flow, because the wavelength is actually compressing even more and more through the duct. So just to say that what I didn't tell you before was that in the analytical model, the mean flow is considered to vary only axially. Okay, so it consists basically on a cross-sectional average in r and theta of the simulated mean flows that you would get with Actran, more or less. Okay, so that's what we get in the model with the variation of the Mach number, sound speed, and density, but whatever. Just to tell you that it was quite different from the simulated mean flow. That's why we didn't have access to this sinuous pattern. So in the end, when we try to identify these modes with the slowly varying modal basis, you see that it's way worse than what I showed you for the other mode. And actually, it is not really able to retrieve the correct mode. In fact, you see here the simulated mode is a little bit less than the radial order above. And there is a lot of other modes that are not way below. So it's very difficult to understand which mode is identified here. So the decomposition is not as clear as previously. And why does it happen? Is exactly because we are in this range in the middle that I shown you previously, where it is more difficult to identify the modes. And why is that? Because these modes are particularly more affected by the effect of the mean flow, because low-order modes propagate in a direction closer to the horizontal axis, so closer to the direction of the mean flow. So they are more affected by it. So if we don't account for the azimuthal distortion of the mean flow, it will be even worse in this range than for the high-order modes that are less affected by this phenomenon. Okay. So if we want to improve in this range of modes, we have to go a little bit further in the modeling. So that's what I tried to do. In the past, I've worked also in the modeling of acoustic modes in ducts and also in curved ducts. And what I remember from that is when you have a curved duct, the mean flow is no longer uniform, but it is, you'll see it is stratified, and it will help us get back to this sinuous pattern. So to tell you how I did that, I took basically the center line of the nacelle wall here, shown in a red line. And you can see that it does not follow the axis, but it bends downward, because the air inlet of an engine is actually a kind of bend downward to be at the right inclination when in flight. Well, doing so, I've rewritten the Helmholtz equation in curvilinear coordinates instead of Cartesian coordinates, still with while accounting for the variation of the cross section. And by doing so, you retrieve this kind of mean flow, which is, as I mentioned earlier, vertically stratified. So you don't have, so you have this vertical stratification, which is already a little bit closer to the simulation in terms of orders of magnitude, let's say. Okay. And what's interesting is that if you look at the view in the cross section, the mean flow is given by a quantity that varies with along the curvilinear abscissa only, and this function of r and theta that is dependent on the curvature of the duct. And so you see the sine theta, and in fact, when you take the value of the mean flow along this circle, you retrieve this sinuous pattern as we had in the simulation that made the plane mode being sinuous as well. So hopefully, it helps us to retrieve a little bit more the plane mode as in the simulation. That's what I show here as a last slide. On the left side, again, the simulation. In the middle, the slowly varying model in a Cartesian coordinate. And on the right-hand side, with curvilinear coordinates. So you can see that we are able to retrieve this sinuous pattern, even if it might need some optimization. But there is pros and cons, because even if we are able to retrieve this pattern, there is also effect of curvature directly on the acoustics. And in a curved duct, the acoustic modes have a tendency to either concentrate at the inside or the outside of the band. And that's why you see here darker spots at the bottom of the duct, which are clearly overestimated compared to the simulation. So it seems to help, but it would need some optimization and see what if it improve or not the identification. Unfortunately, I didn't have time to do that yet. So stay tuned for a next seminar in a few months at the end of my postdoc if you want to have new results. Okay, so just to summarize a few key points. We've seen that the complex mean flow in this kind of reduced nacelle inlet is complex and three-dimensional. We've tried accounting for the axial variation of the duct geometry and mean flow through slowly varying formalism from Rienstra's model to improve the modal identification. Generally, it performed better than the classic duct modes, especially when transition occur. We needed Tikhonov regularization to identify the modes, especially at low order. And finally, we tried to retrieve this azimuthal distortion of the mean flow to have the axial variation and azimuthal variation. And this seemed to help retrieve the sinus pattern that we wanted, but we didn't check it more than that. So future works involve, of course, modal breakdown with this new model, which is the one of Bromley and Pix mostly, and try to apply this methodology to experimental data, or at least more realistic simulation. And that's it for me. Thank you for your attention. And if you have any questions, feel free to ask.
Thank you for this nice presentation.
Merci.
Yes.
Yeah, go on. Go ahead.
We're talking about the technique of slow varying modes. Are we considering only different geometries or any change in shape?
Geometry and mean flow. That only happens, I don't have any slide in fact, but that only occurs along the axial direction.
Just like this, or can it change, like it goes bigger, then it goes...
It can change in any ways, as long as it does it slowly. So you can have a drastic difference between the inlet and the outlet of your duct, as long as the duct is long. Because you want, in fact, what matters is not the change, but the rate of change. So you want the wall, as I mentioned, to be assumed parallel to each other. Okay. As long as you can do that, you can use this approximation. This is an approximate solution.
In slide 11?
Yeah, it reminds me of my defense.
Yes, this modal decomposition.
Yes.
This side nodes, how we know that it is not, it is a scattering, mode scattering, or a leakage, spectral leakage for the decomposition?
From the decomposition? Alors, the scattering, when I talked about scattering, I was mentioning what happens in the simulation, right? What happens in the identification when we try to project this pressure data on the model basis is that the model is not able to retrieve, it cannot find some composition of modes that generate this pressure field.
Yeah, but I think this is scattering already existing in simulation. I can see.
Yeah, here there is several modes.
So we did the projection, and this is the model.
Yeah, I did the projection on the black circle and reconstruct the pressure field with these identified modes, and that's what you get with the classic duct modes without any geometry variation. This one?
The big one. It's a leakage or scattering. Leakage is a numerical problem.
Yeah,
Scattering
yeah.
is a physical
You mean for this mode there? Or which one? Which ones are you talking about? Sorry.
on the side.
Here?
One mode. You're saying that it's one mode, 5.
Yes.
1.4. So we should see the projection is accurate.
Only a single mode. Single mode.
So the other are.
The others are none of them. We don't retrieve the correct mode because mostly because the model basis is not able to retrieve this mode because it does not correspond. Since we do not model the same mode, it tries to reconstruct the pressure field with a composition of different modes, and the composition that is found to be the best is this one, which does not correspond to the one we are looking for. Tikhonov regularization.
The other question.
Yeah.
Slide 17.
Maybe let's sum for the others.
Yeah. What are the modes in the middle? Here you simulated.
Yeah. The modes in the middle are low order modes, so basically fundamental mode and low azimuthal and low azimuthal modes, basically. No, the only simulated modes are -40 and 70. So that's an error of identification. Yeah.
Again, numbers.
Yeah.
Slide 16. Yes. Yeah. The phenomenon of contraction of the example, is it the same as convection? Because we know how new the
This is not convection, no. The acoustic waves propagate, and the wavelength that they have is compressed by the mean flow if they propagate against the flow, or extended if they propagate in the direction of the mean flow. That's a Doppler effect.
Okay, this is what is called convection? Or
No, convection is the fact that a quantity is convected by the mean flow. This is another.
Yes, this decomposition on the right, it seems like it's yes, it's replicas.
Replicas? Ah, yeah, because what I didn't explain is that you see from 250 to 256, maybe a little bit more. This is a group of same azimuthal order, but different radial orders. So what you see is three groups of three different azimuthal order, 0, -1, +1, and different radial orders inside. Yeah, yeah. I didn't want to go because it's not easy to make a representation clear, but understand that the group in the middle is azimuthal order n equals 0. This group is n-1, n+1, and the different bars is different radial orders. Yeah, sorry for that. Yes, Thomas, peut-être.
Very naive question. You said right from the beginning that the flow was non-axis.
Yes. Yeah, sorry. And this is understand that this is a potential flow simulation. So in reality, it's even more complex. Yeah, yeah. I could have spent more time here. So how to see if it's non-axis symmetric is to look at the difference between the top and the bottom. At the very beginning. Here. Ah, this the slope of the mode is the direction of propagation of this mode. So because of the azimuthal order 5, it is a spinning mode. So its wavefront is inclined. Yeah.
even here there is some non-axis symmetry?
In the simulation, for sure. It's not very apparent, but for sure there is, yes. The most... Yeah.
When you say that the simulation is the truth,
There's the reference. It's not... Theory. Yeah, no, definitely not the reality, but the best reference that I had here, again, the potential flow is also a very big simplification of reality. Go on.
You're deep in the subject, and I know nothing about it.
Yeah, okay. Don't worry.
If I look from, let's say, a classical acoustic point of view, you have here a space which you call a duct, okay? With non-conservative boundary conditions, with flow, and a quite challenging problem of describing the sound propagation. And for doing that, you use what is an approach which is very familiar to many acousticians, which is the modal decomposition approach. Now, in doing this, by your analytical model, you neglect the convection effect, you neglect both effects, and you explain later the results by taking into account the flow. But then, in the classical sense, the classical model approach, which then brings all the advantages of classical model approach, like model orthogonality, etc., which also assumes proves that the energy in each mode is independent of other modes. All of these assumptions are violated here because the basic assumption of model decomposition are violated. I believe you said the your Mach number is about 0.2.
0.2, yes. In fact, this is the outside Mach number. So the Mach number of the flow inside the duct is more 1.4 to 1.5. 0.4 to 0.5. Yeah, 0.4. Yeah, quite high. No.
So in such a case, normally modes will not share the energy independently. The boundary conditions will all different. So the question is, we have right to use the notice of the model approach, or we just about different modes of application. But let's say this is you did explain findings by both your analytical model and using numerical model, and you did explain the discrepancy which orthogonals, I can say, model that approach would review. Now, it seems to me that really a decisive step from the point where you are now would be to make comparison with this work. Because there are so many assumptions included here, rather brave, but this is what is the question of today, to be brave.
Yeah.
Europe is sending 6 So I think that very simple would be to make experimental validation, not to, I would say, not to put in question the analytical model. It will surely be useful, providing the one is the third understands its limitations and its constraints. So, how how far in experimental work can one go in your field? It is because experiments tend to be very expensive.
Yes, in fact, there is a. We should have had already results of an experiment. So, why I've used this geometry and exactly this microphone array for the location of the pressure that I took in the simulation is because there is, this is inside the European project, Clean Aviation Companion, where within this project, an experiment in wind tunnel will be done, and also experiment in flight with along others, acoustic measurements with a panel of microphones glued to the fuselage on the side of the engine. So we will have in the future, and we should have already, but there has been delays, experimental results where we have a lot of flow measurements without acoustics, with a lot of probes inside, and also measurements for the acoustics with less information about the flow. And that should be our true reference to see whether or not this work is able to help or not. Unfortunately, we don't have that yet, so that's why in the meantime, we worked with simplified data that have been simulated. The idea was first to use Actron simulation because it's the closest to the simple analytical model, where we can see each mode individually at each frequency and see, you're right, not a real model breakdown, but more to say if we have the right shape of the modes compared to what we see in the simulation. Then going to a more sophisticated simulation to see if it works with a more realistic flow before applying it to experimental results. So the only truth will come from the experiment for sure. I just want to also maybe say something about the model. There is a mean flow. I just didn't put it in the equation for sake of simplicity, but when I apply it for the modal decomposition, there was a mean flow uniform like this, what we see in the middle. So the mean flow is always here, just it is more or less simplified. And my approach is on the other side of experimental. So in the experiment, you go from the more complex case, which is reality, and you try to understand what's going on inside. Here I go from the bottom, the most simplified case, and I try to go upside to see at which point we reach together. And I don't do that alone. There is also a numeration in the project, experimentalist that goes the other way, who go the other way. So that's a group effort to have to converge to the right solution in the end. If it answers your questions.
Question, saying the phone is what temperature, total temperature, what
Total temperature is accounting also for the kinetic energy, temperature plus half of rho v squared. This is something we use. I couldn't know that with one. Sorry. This is the total temperature outside of the engine. So where there is no mean flow, so it's equal to the static temperature. So it's 300 K. Exactly. So that's exterior Mach, exterior temperature and pressure. But since we consider in this simulation conservation of the energy, of course, the total temperature and total pressure remain this inside the duct, but with some part of it in kinetic energy, so the static temperature and pressure would be less inside the engine. Yeah, exactly. I just put, if you want to, it's the boundary conditions on how to set your simulation.
said that the model gave the mode, and you gave numbers, which normally would be real wave numbers for propagating modes, imaginary or
Yes.
but they may be different.
Yes, they are in fact, because of the mean flow, we have complex numbers with a real part and imaginary part when they are propagating, and only imaginary when they are decaying, cut off. Yeah. Yeah, sure.
Thank you. So the next seminar will be given by Anne-Sophie Poudrel on the 5th of February. So if you want to give also a seminar, you're welcome. Just tell me.
Yeah, do a seminar.
Thank you.
Thank you.